Hello, everybody. So this video, I want to recap what we did before our extended break and just kind of get back up to speed and quickly review what we're going to start with when we start talking about quantum mechanics properly. Um, so the general idea was that we were talking about both light, which normally acts like a wave, acting sometimes like particles, and also that sometimes particles, like electrons, protons, neutrons, whatever, also seem to be acting like waves. And so the big important relations that we used there was the de Broglie relations. So the idea was that the wavelength of this would be Planck's constant divided by the momentum. And we similarly had that the frequency was basically, I'll write it this way, h times the frequency is equal to the energy, or frequency is energy over h. And so those were the postulates that de Broglie came up with just to try to figure out what was going on with things. But now we want a wave equation. And if you go to the other video where I reviewed the classical wave equation, we sort of saw a little bit of how that works. But here we can put together what we know about quantum, kind of what we want the solution to look like, and a little bit of what we know to kind of at least get a pretty good guess of what this wave equation is going to have to look like. So some further notation review is that we said that this wave that everything is some kind of, we'll call it a wave function. Capital psi, it's a function of position and time. We will often break it up into just a position part, lowercase psi, and maybe a time part, phi there. We'll use that by by definition and solve the differential equation that way. And we said, what is this probability? What is this wave function? I mean, what's actually waving? We said that we were going to think of it as kind of probability, but it's not the wave function itself that's probability. It's the magnitude of its squared that's the probability. So we have something like magnitude squared is the probability. And here I've written it as position and time, but we don't really want probability of finding a particle to change over time. So usually we're just worried about the position part there. But and that the wave function itself can be complex, can be complex numbers, because that way it can oscillate and still have a, when you look at the probability, it's still one everywhere, but it's still oscillating. It's kind of going around in circles like a jump rope or something. That is sort of the picture we had. So this was kind of where we left off. Other important things that we're going to need are that, remember that we did say waves, if we want waves to be a solution, classical waves look like, you have something like this, where it's a sine or a cosine or whatever. There can be some phase in there. That's not too important. But there's, the wave number times x minus omega t. And remember, the definition of wave number here is just that it's really inverse wavelength. K is 2 pi over lambda, just like omega is 2 pi over period of the wave. So we'll be using that notation again quite a bit to kind of figure out what's going on. Other things to review are we will still use sometimes the relativistic notation, especially when we're talking about light, where for light we have that the energy is just equal to the momentum times c, and we can do a lot with that. In general, we have a more complicated, that the total energy squared is bc squared plus mc squared, all of that squared. We'll occasionally come back to that. But for most of the next part of the course, we'll actually be doing what's called non-relativistic quantum mechanics, where the actual wave that we're talking about will be a wave of a particle that is not moving relativistically. But this is kind of where we stopped off, so this is just a refresher, hopefully. Still fresh in your mind, but this is where we're going to pick up again. We're going to figure out what is this wave function. We're going to find a differential equation that is our wave equation, and then actually solve for these waves, and not just get sine functions, but get different things depending on what's going on. And that is where we are about to go next.